So, there's this really powerful story you've probably heard about the future of humanity. It goes something like this. AI is getting crazy fast, and for us to have any hope of keeping up, we need to upgrade ourselves. The main problem, we're told, is a bottleneck. It's a bandwidth problem.
And this quote, it just nails the argument perfectly. It paints this picture of a massive speed difference, right? A world where humans are basically obsolete unless we can somehow directly merge with the tech and crank up our own data speed. And yeah, when you look at the raw numbers, the gap looks absolutely massive. On one hand, you've got AI zipping along at terabits per second, and on the other hand, there's us, with our conscious output, talking or typing, clocking in at maybe 10 bits per second. So the whole problem is framed as this urgent, almost do-or-die mission to close that gap.
Okay, but let's just stop for a second, because this is the big question. Is the solution really to just pump more data into our brains? Or is it possible this entire narrative completely misunderstands what a brain actually is and how intelligence even works?
To really get a handle on this, we've got to start with the basics, with the hard science of what's actually happening inside our skulls. What do the brain's electrical signals really look like from a pure physics standpoint?
Now, what's fascinating here is the scale. A single neuron firing gives off a pretty clear voltage spike. But by the time all those little signals add up and travel through your brain tissue and your skull to be picked up by an EEG on your scalp, they are incredibly weak. We're talking microvolts. And the magnetic field? It's even tinier. And this really gets to the heart of it. Your brain's electrical field isn't a powerful signal designed to send information like a Wi-Fi router. It's more like a byproduct of all the activity, kind of like the heat coming off your laptop. It's localized, it's messy, and it is very, very faint.
So even when we can measure the brain's general rhythms, its alpha waves or gamma waves, that's not the same thing as actually understanding the information being processed. It's like hearing a crowd chanting from a block away. You can hear their rhythm, you can tell they're all in sync, but there's no way you can make out the actual words they're saying. See, frequency and content, totally different things.
And that leads us right to this fundamental problem in engineering, this signal-to-noise ratio. To hear the specific words of individual neurons through all the background noise of your skull and tissue, you need a crystal clear signal. And right now, the only way to get that is to get your sensors really, really close to the source. That, right there, is the main reason today's most advanced brain-computer interfaces have to be invasive.
And we have to be super clear about this. For helping people regain lost function, this technology is nothing short of a miracle. Helping someone who's paralyzed control a computer cursor or a robotic arm is a life-changing breakthrough. The point here isn't to knock that amazing work at all, but to ask a different question. Does that same approach work for cognitive enhancement?
Okay, so if the physics shows us our brain signals are actually weak and noisy, then you gotta ask, is the problem really about getting more data in? Let's take a look at where the real bottleneck is, because all the evidence suggests it's not our input bandwidth. It's actually our brain's unique processing architecture. Just think about it for a second. Right now, your eyes, your ears, your skin, they are all taking in a gigantic flood of raw data from the world around you. Your brain is already getting fire-hosed with high-bandwidth information. The real magic isn't in how much data it gets, but in what it does with it. The very first thing that happens is that massive flood of data hits a really powerful attention filter. Your brain is actively throwing out almost everything to just focus on what it thinks is important. And that's not a bug. It's a core feature of how we manage to make sense of a really chaotic world. And whatever makes it through that attention filter then runs into the next bottleneck, your working memory. This is basically your brain's scratch pad, and it's tiny. It can only hold like 7 concepts at a time, give or take. It's an incredibly narrow pipeline.
And finally, the brain doesn't just filter the data. It does something amazing. It compresses all of it. It weaves new information into mental models, connects it to things you already know, and actually creates meaning. This whole process, that's what we call understanding.
So you see, that massive flood of sensory data gets processed down into this tiny trickle of conscious thought. This extreme data reduction isn't a flaw in our design that needs to be fixed with more bandwidth. It is the design. It's how we build a stable, coherent reality for ourselves.
And this brings us to the core idea of this whole explainer, a concept called receiver-limited integration. All it means is that the real limit on our intelligence isn't the size of the data pipe coming in. It's our brain's very limited ability to take in, compress, and actually make sense of that data. Let me say that again, because it's so important. Intelligence is not throughput. It is structured reduction. Just jamming more data into a system that's built for compression doesn't make you a genius. It just creates a lot of noise. It's like trying to fill a coffee cup with a fire hose.
So, if blasting our brains with a high-bandwidth fire hose is probably the wrong approach, what does a more realistic and frankly more effective future of human-AI collaboration actually look like?
Well, you can kind of see the future splitting into two different paths. The invasive merge idea is all about forcing more bandwidth into our brains, which basically means making humans adapt to how AI works. But this runs into a huge problem that's even bigger than the surgery itself. Our brains are all different. The way your brain represents the idea of blue is totally different from mine. This means every single implant would need constant personalized tweaking as our brains change over time. That alone makes it incredibly hard to scale up.
But the communicative partnership model looks totally different. Imagine a wearable device that can accurately figure out what you're trying to do and then feeds that to an AI partner that acts like your co-pilot. The goal here isn't to cram your brain full of data, it's to reduce the lag between your thought and your action, to make technology feel like a natural extension of yourself. In this future, the AI works with the brain's limits and adapts to you, which completely sidesteps that whole scaling problem.
So what's the big takeaway here? What does this all mean for the future that we're all building together? Let's tie it all together.
At the end of the day, it all boils down to one simple truth. The ultimate gatekeeper of information and insight is you, the human receiver. Your ability to create meaning and keep your thoughts coherent is what matters, not how fast the data is coming in. And any technology that doesn't get that is probably going to fail.
Invasive BCIs are and will continue to be an incredible tool for therapy and restoration. But for the rest of us, the real path forward for enhancing our minds has to be built on a deep respect for our biology. We should be building tools that work with our strengths, not tools that treat our very nature like it's a bug that needs to be fixed.
And this leaves us with one last, really fundamental question. As we design this next chapter in our relationship with technology, what's our guiding principle going to be? Should we try to re-engineer ourselves to fit the machine, or should we demand that our machines be built to fit us? The choice we make is going to define everything that comes next.